Welcome to CBS Easy.
Welcome! You ever feel like life is just a series of little puzzles? Well, it turns out that algebra, the stuff you might remember from a classroom, isn't just about X and Y. It's actually a super powerful playbook for solving those very puzzles. And today, we're going to see exactly how.
Okay, let's dive right in. A scene just like this, say at a local fair, is absolutely packed with hidden questions. How many rides can you actually go on? How many games can you play with the cash in your pocket? These aren't just random guesses, you know? They are problems that have real, concrete answers. And today, we're going to learn the playbook for finding them.
So, what's on the agenda? We are diving into 5 totally distinct challenges, and each one is a classic puzzle in its own right. We'll start with tickets, then we'll move on to money, a tricky little fraction, a speeding train, and even a riddle about ages. And here's the really cool part. We're going to crack every single one of them using the same powerful tool. Now, that tool at the heart of our playbook is called a pair of linear equations. I know, it sounds a little technical, but the idea is actually really simple. We have 2 unknowns, let's just call them X and Y, and we have 2 clues about them. Our goal is to find the one single value for X and Y that makes both of those clues true at the same time. And our secret weapon for doing that is a method called substitution, which we're going to see in action right now.
All right, let's put our playbook to the test with our very first puzzle. This one's a classic scenario that you've probably been in before, whether you realized it or not, right there at the ticket counter.
So here's the challenge. We're given 2 key pieces of information, the grand total of tickets and the relationship between the 2 types of tickets. Our first job, we've got to translate this story from plain English into the language of math.
And what's so cool about this is how we can systematically break the problem down. First, we assign our unknowns. X is for adults, Y is for children. Simple. Then we build our equations. Equation 1 is the total. X plus Y equals 120. Equation 2 is that relationship. X equals 2 times Y plus 20. See? Nice, manageable pieces.
So using that substitution method, we take what we know about X from that second equation and we just plug it right into the first one. After a tiny bit of algebra, the numbers just fall right into place and we get our clear answer. The cinema sold 87 adult tickets and 33 child tickets. But let's check it. Do they add up to 120? Yep. Is 87 20 more than twice 33? Yes, it is. Both conditions are met. Problem solved.
Okay, 1 down, 4 to go. Our second puzzle takes us from tickets straight to cash. Now this is a situation where being precise with our numbers is absolutely crucial, and our playbook is perfect for it.
Do you see the pattern here? Just like with the tickets, we have a total amount and a specific relationship between 2 people. The story is different, sure, but the underlying structure is identical. So let's apply our playbook and translate this thing into equations. And this just illustrates the pattern so brilliantly. Step 1, identify your unknowns. Ravi's money is X, Sita's is Y. Step 2, what's the total? X plus Y is 1,500. Step 3, define that relationship. X is 2 times Y plus 300. It's the exact same logical flow. We followed that same substitution method, and the math leads us right to a clear solution. Ravi has 1,100 rupees, and Sita has 400. Together, is that 1,500? Check. And is Ravi's amount 300 more than twice Sita's? You bet. Our playbook works like a charm again.
Okay, now for something a little more abstract. Our third puzzle moves away from tangible things like tickets and money and takes us into the world of fractions. But as you're about to see, the underlying logic is exactly the same.
Now, this one might sound a little more mathy, but trust me, it's the exact same logic we have been using this whole time. We've got a sum and we've got a relationship. That is our cue.
And here's where we really see the power of this method. We're just swapping out words like tickets or money for numerator and denominator. Let's say the numerator is X and the denominator is Y. Our first equation is their sum. X plus Y equals 12. And our second equation? It captures the relationship. X is 2 less than Y, or X equals Y minus 2. We plug those 2 equations together and boom, out comes the answer. The numerator is 5, and the denominator is 7, so our mystery fraction is 5 over 7. Let's do a quick check. Is their sum 12? Yes. Is 5 2 less than 7? Absolutely. Perfect. All right, now for our real classic, a puzzle involving distance, speed, and time. This one adds a little twist to our playbook, and it's going to force us to think about 2 different scenarios. The challenge here is that we aren't just given two simple sums or relationships. Instead, we have to think about how speed and time are fundamentally connected when you're covering a fixed distance. We basically have the original journey and the what-if journey.
Now, what's really interesting here is how we translate those two scenarios. The original journey is pretty straightforward. Speed times time equals 240. But the faster journey is speed plus 10 times time minus 1, and it also equals 240. Setting up these two distinct equations, that is the absolute key to solving this thing. Now, I'll admit, the algebra to solve this one is a little more involved than our last few examples, but the setup, that's the magic of the playbook. Following it through, the math tells us that the train's original speed was 30 kilometers per hour. Getting those two scenarios translated correctly was the whole game. For our final challenge, let's tackle one of the most famous types of algebra problems there is, figuring out people's ages by looking at the present and the past.
The key to cracking this one, the real trick, is to correctly handle two different points in time, what's true right now and what was true 5 years ago.
And this just brilliantly shows how to represent the past using math. We defined f and s as their ages today, so f plus s equals 50. Easy enough. But for the second equation, we have to look at their ages 5 years ago. So the father's past age, f minus 5, was 3 times the son's past age, s minus 5.
Once we have our two equations, one for the present and one for the past, we can solve them to make the timeline crystal clear. The father's present age is 35, and the son's is 15. Let's check it. Do their ages add up to 50? Yes. And 5 years ago, they would have been 30 and 10. So the father was indeed 3 times the son's age. The math perfectly connects the past and the present.
So what's the ultimate takeaway from all this? Well, it's that the real magic isn't just in finding the answer. The most powerful skill is learning how to translate a confusing story, whether it's about tickets or money or time, into a simple, clear, solvable set of equations. That is the playbook. And it's how you bring clarity to complex problems, not just in math, but in pretty much any part of life.
Thank you for watching with us. See you next time.